Hi, my name is Steve Mackay from Engineering Institute of Technology. Going to do a quick presentation on industrial safety, emergency shutdown, risk assessments, and obviously some comments about safety instrumentation. So hopefully you get this in a few minutes. We provide you with a full set of slides, so please feel free to grab those. I don't want to bore you with extraordinarily drawn-out dissertation over a few hours, so we'll keep it short to about 10 minutes, maybe shorter, maybe longer, and really look at safety instrumentation. So we run these courses every few weeks and try and release a recording at least once a week, just to try and put something back into the marketplace. Really just to give you some hopefully useful information. Obviously, if you want the full book, or you need to obviously do some research. They always say an expert is someone who spent 10,000 hours studying a particular topic, whether that's a brain surgeon or whether it's a process control engineer. I think 10,000 hours is a pretty good summary. It's a ferocious amount of time. Obviously, this is not anywhere near 10,000 hours. Let's have a quick look where we are with safety in the process environment. Here's a few case studies of things which went badly wrong. Warm, sunlit afternoon in England, which is probably a little bit of a contradiction sometimes. Well, I've been here for the last 3 weeks in the middle of December, and of course it was sunny every day, much to my surprise. So the first one is Nipro Chemical Works, Fixborough. Cyclohexane vapor cloud ignited, 28 killed. So again, poor piping design by a poorly qualified design team. So really what you're saying here is you can certainly use this technology, which I'm going to talk about now, to try and pick this up. But obviously, at the end of the day, it's up to the designers of the entire system to make sure that you don't get put into this position in the first place. So temporary piping design is a big issue. Having a control system to pick up the problem is really perhaps a little bit later after the event. So it's really not a preferable scenario, but obviously it does give you that safety protection. Another example is Ex Misa, Seviso, Italy, 1976. Again, TCP, disinfectant. Exothermic reaction caused pressure buildup and release of dioxin byproducts. So pretty horrendous problem there. So again, to be avoided, I think TCP is actually carcinogenic. 3 Mile Island, the good old nuclear hazards, and obviously most people are very jumpy about nuclear reactors, and I suppose if you think about Chernobyl in Russia, got reason to be concerned. So here we had inadequate control room instrumentation, poor emergency response. No injuries or deaths, but you can bet your bottom dollar, American dollar that is, that there were potential injuries or illnesses as a result of this release. Another example is Bhopal, which is pretty horrendous. 4,000 died. Large amount of water got into a storage tank, and you had a chemical reaction, exothermic reaction, exploded the storage tank. So basically you had cyanide released into a very poor town, 900,000 inhabitants. Absolutely horrendous situation. I reckon the CEO of Union Carbide was so traumatized. He was a very successful individual, but after this he basically semi-retired. Not that it helped the 4,000 that were killed in India. Milford Haven, UK. Texaco refinery. Funny enough, soon after we ran a course there actually. Horrendous alarm overloads, and again, pretty bad explosion. Sonat Exploration Company. No plant operating procedures, inadequate vessel release devices, and absence of any process hazard analysis. So overpressurization, 4 killed. Another one is BP Refinery, another famous one, 23rd of March 2005. Again, pretty bad explosion there. And obviously the question is, can it happen to us? Well, it certainly can if we're going to do something about it. So just here are a few little basics of the system, whether it's an emergency shutdown system or safety instrument system, what do you want to call it. First of all, we use the abbreviation SIS, Safety Instrument System, often referred to as a shutdown system, instrumented protection system. Everyone has their own little acronyms, as we all do. And this is an example of a functional safety system. Again, I emphasize this fixes or tries to prevent damage or hazard after the event. Obviously, the entire holistic design needs to be done properly from the beginning. So, and this is obviously related to 61511 standard and the 61508 standard. So really in a typical control loop, which we're all familiar with, you've got a PID control loop. You've got on your left, you've got the good old flow meter, and on the right, you've got your control valve. And in the middle, you've got your PLC controller, DCS system, standalone loop controller. And as you would see from this, there's nothing really to pick up a potential hazard. Obviously, you're designing this so you don't have a hazard, you don't have a overflow or over level of the tank. So the idea is that you put in a protection system here running in parallel, which picks up the potential problems and corrects for any problems independently of your control system. Obviously, the idea is the control system will also act properly, but this acts as a sort of big brother pick up of problem. So here's a typical safety instrument system with sensors. So you've got eyes, logic solver, and then actuator. So you've got a user interface and then the basic control system over here. And then you've got your three subsystems. The sensors, the logic solver, and then your actuator. What do you do? So just a few issues. The system basics. Obviously, the risks are due to the presence of a hazardous process or procedure. And a hazard is defined as an inherent physical or chemical characteristic as a potential for causing harm to people, property, or the environment. So obviously that's what we've got to assess. So a hazard really is what is the potential problem, and then there's an issue called risk. So when you have the severity, which is how bad is it, and the probability or the frequency of the event, multiply those together, you get a risk. So obviously we want to try and keep that as low as possible. So here's a simple shutdown system. Don't worry too much about that. Vapor hazard. So obviously we want to avoid overflow with this system. Shutdown system. So risk reduction is reduce the frequency and reduce the consequence if you can. So that's assuming you can't remove the hazard. So a typical example is you can have risk which is high, low, or moderate. So, for example, quantitative 1 in 10 years, 5 people get hurt. So here's the example of the risk, which, as I said, is the consequence multiplied by the frequency. So you could have fatal, serious injury, minor injury. So obviously the idea is to try and reduce the risk as much as possible. So the idea is reduce the risk, consequences, and the frequency. Try and make sure that it happens very rarely. So if you can't change the hazard, you can actually look at reducing the risk of it happening, the actual probability. So risk reduction design principles, as we indicate in the diagram: identify the hazard, look at the risk reduction requirement, RRR, and then establish a tolerable risk, and then you target your safety instrument at So as I said again, it runs independently of your control system. So the amount of risk reduction allocated to the SIS determines its target safety integrity level, its SIL. So it tells you what level of risk. So for example, here we've got safety integrity levels from 1, which is very low, to 4, which is high. So basically, the risk reduction factor for level 1 SIL is greater than 10, less than 100. So we'll give an example of that in a tick, all the way to 4, which is 10,000 to 100,000. So probability of failure is very, very low. So safety integrity level gives you the level of confidence placed in the ability of the system to provide functional safety. So what does SIL mean intuitively? For example, you have a SIL of 1. You have a safety instrument system with availability of 90%. You say that's acceptable. High level trip in a liquid tank. So in other words, there's a 10% chance of failure. 1 out of every 10 times the high level is reached, there would be a failure, which means you have to overflow 1 out of every 10 times you're in that position. So that's a SIL of 1, 10 to 100. Pretty low. And obviously, if you're dealing with something pretty bad, you will find SIL of 1 is completely unacceptable. Okay, that's really just a quick run through on emergency shutdown, safety instrument systems. Any questions, shoot them through to me, Steve Mackay. Thank you very much for listening in. And I will be calling it quits at this point. Thank you very much.